Look at the physical world around us. When we measure the speed of a car, the temperature outside, or the mass of an apple, we always get a real, tangible number. But if you zoom in and look inside a quantum computer, things work differently. Here, information is processed using tiny components called qubits. The math running these qubits relies heavily on complex numbers, which include an imaginary component. This math is perfect for describing subatomic waves, but you cannot measure an imaginary number with a physical ruler or a standard thermometer. So how does a scientist ask a quantum computer for a real-world physical measurement, like energy, if the computer calculates everything using imaginary numbers? To bridge that gap, we use a mathematical translator. It is a specific type of grid called a Hermitian matrix, and its entire job is to guarantee that the final output you receive is always a real, usable number. This animated diagram shows a 2x2 matrix, a grid of numbers used to process data. Notice how this specific grid has a mix of regular numbers and complex numbers containing an I. To test for a Hermitian matrix, we put it through a two-step mirror test. First, we imagine a diagonal line cutting through the center, and we flip the grid by swapping the numbers across that line. Next, we look at the complex numbers that just swapped places, and we flip their mathematical signs. If a number had a plus sign, it becomes a minus. Now, look closely at the result. If after that double flip, our grid looks exactly the same as the original grid we started with, we have a confirmed Hermitian matrix. That rigid, unyielding symmetry is the exact mechanical structure that gives the matrix its translation power. This diagram shows our verified Hermitian matrix again. Let's focus on that main diagonal line glowing down the center. For the mirror trick to work perfectly, every number sitting on this center diagonal has to be a purely real number. There can be no imaginary parts here at all. Now look at the numbers reflecting each other across that center line. They are perfectly balanced opposites. They are completely identical, except one has a positive imaginary part and the other has a negative one. Compare that to a completely different grid, trying to do the same trick. If the numbers on the sides are mismatched, they clash when they flip. The math breaks and the mirror test fails. This perfect balance of real anchors and opposite reflections acts like a structural lock. It ensures that when the computer does its work, the imaginary parts are always forced to cancel out. This animated diagram shows what happens when a quantum computer actually measures something, like the energy of an atom. It passes a messy, complex quantum equation into the top of our balanced Hermitian grid. As the calculation runs, the structure of the matrix goes to work. Those opposing imaginary pluses and minuses attract, mathematically collide, and cancel each other out entirely. The matrix finally drops a clean result out of the bottom. This is what we call an eigenvalue. Think of it as the actual value that was hidden inside that complex math. Because those mirrored sides did their job, this answer is guaranteed to be a solid, real number we can actually use. Without this mathematical mechanism cleaning up the output, our quantum technology would speak a language completely incompatible with human engineering. Hermitian matrices take the complex language of qubits and safely deliver the reality we can actually measure, understand, and build upon.